For an isotropic material, the shear modulus G and the bulk modulus K in plane elasticity, that is plane strain, are related to the well-known Young's modulus E and the Poisson ratio νi in the following way. If the material we are considering is, for example, a plate, then we use plane stress instead. Then we have the same expression for the shear modulus G, but the bulk modulus is a little bit different. An orthotropic material has the property that it is symmetric with respect to three orthogonal planes. So what does this mean for practical purposes? Well, it means that if we subject the structure for any type of deformation, the stress response will inherit this symmetry. For example, if we let this red plane, x2, x3 plane, be the symmetry plane. Let's see what's happening then. If we stretch the structure in the green direction, we will obtain exactly the same energy as if we stretch it in the blue direction, which is symmetrically on the other side of the plane. A structure which is orthotropic with respect to the shown planes will have the following stress-strain relation. Here we have the strain vector. These three strains, the upper strains, are normal strains, and the lower three are the shear strains. And here we have the stress vector. And here we have the stiffness matrix. For convenience, we call this stress vector sigma and the strain vector E. And we call this stiffness matrix just capital C. Note that in a composite material, the coefficients in this stiffness matrix are dependent of the spatial coordinates. So it will not be constant in each point. It will be a different value. Therefore, we want to find the effective stiffness matrix, which is not dependent on the spatial coordinates, but is just constant. This matrix is formed by considering the following average stress-strain relation, which describes the relation between the average strain vector and the average stress vector. The average is taken over a representative volume element, which is large compared to each fiber, but at the same time small compared to the whole structure. The local stiffness matrix will vary from point to point. In this case, it will take two different values, one value inside the fiber and one value outside the fiber in the glue or the matrix as we call it. In this case, the material will effectively behave as an orthotropic material. In fact, it will be plane isotropic. stretching the material in one direction will be just as heavy as stretching it in another direction, for example. Roughly speaking, the effective stiffness matrix C star is the stiffness matrix of a homogeneous material with the same effective properties as the actual composite material. For example, this means that the energy stored in the composite material, in for example this little square on the picture here, will be exactly the same as the energy stored in the corresponding homogeneous material with these effective properties. Let us denote the representative volume element by capital Y. Then we have that the energy stored in the composite material can be written as the following integral. And this energy should be equal to the energy stored in the corresponding homogeneous material with the same effective properties. So then we have that these two energies are equal, and we have the following equation. The latter integral, which is the energy inside this representative volume element, is the integral over a constant function. All the variables here are constant, so we can just integrate it. It's very easy to integrate a constant function. It's just what's inside the integral multiplied with the area of the representative volume element, capital Y. And we denote this area by this absolute value of Y. Here is an example. Let's compute this value. C1111 star is found by considering the effective stress-strain relation. In order to find this value, we put the average normal strain in the one direction equal to 1, and the other average strain equal to 0. So then the average strain vector looks like this. This means that we have stretched the composite material in the one direction, so that the average strain, normal strain in that direction is equal to 1, and all other average strains are equal to 0. We then measure the average stress vector. In particular, we are interested in the first element. Substituting these two vectors into the average stress-strain relation, we just obtain the following. So, using this simple equation, we obtain the value by computing the average value of the normal stress. Alternatively, we can find this element C1111 star by computing the strain energy contained in this cell Y. And this can be measured, or it can be computed, for example, by using ANSYS. On the right hand side of this equation, we just implement the average strain vector and the value of the area of the Y cell. I'm doing this a little bit fast for you here. Multiplying this 6.6 matrix with this vector, we obtain a new vector, and taking the scalar product of this vector to this first vector, we obtain easily the following expression, and half multiplied with the coefficient we need to find. And of course we need to multiply it with the area of this cell Y in addition. Calling the energy for W, we know that C11 star is just equal to twice the energy that we have measured or computed. We also should mention that the stiffness matrix is always symmetric with respect to the diagonal. The elements of the stiffness matrix are related to the classical average Young's modulus in the different directions and the Poisson ratios in the following way, which we are not going to prove here. It's also possible to show that the inverse of the effective stiffness matrix is given by the following expression.